my name is Frank. I'm working at a company called Vision and Robotics, and I'm here to present our entry to the SLAM Challenge. Our company was founded in 2008. It was a spin-off of the University of Koblenz in Germany. And initially, we were a robotics startup, but then transitioned into solving general computer vision, AI, and SLAM problems. Sorry, I have some issues with my voice, so excuse me. We're a team of around 15 people, and we run a pure business-to-business business. So we license our custom software modules onto our customers, and we try to help them solve difficult problems at the edge of research. We don't actually build hardware products, but we do build hardware prototypes to showcase our technology, and you can see that on the next slide, some of the prototypes that we've been building. And in general, we are looking for partners that are interested in deploying our technology into actual products. We have a general focus on LiDAR and IMU-based SLAM because we believe it is the most accurate way to do SLAM at the moment, the most robust way. And we're striving for physical plausibility. So we're trying to calibrate everything correctly, do tight fusion, and make sure we don't have any jumps, for example, in the trajectory, so that everything is physically accurate. Our use case is generally surveying over robotics. So we try to obtain the most accuracy from our result, and we don't strive so much for the real-time use case that some roboticists are interested in. Our solution is comprised of two stages. In the first stage, we do real-time SLAM in order to obtain an initial solution. And then in the second stage, we perform loop closing and global optimization to refine the result. This first stage in real-time SLAM, you can see some video from one of the challenge data sets down here. This is it performing SLAM. And there are also some screenshots showing results from the challenge and some results from our own data set. Our algorithm is based on our MC2 SLAM algorithm. This is published and linked up there. And it does basically overlapping registration of subsequent scans against a local map. And it undistorts the scan and performs typed factor graph-based IMU fusion. Here's some more impressions down here in the video. So, it is switching to another visualization mode now, so that you can see it from another perspective. Then we perform global optimization. This is in general a joint optimization of the whole trajectory, IMU, biases, and map. And we're generally able to fit all of the available measurements. Sorry. We do not treat any sections of the trajectory as fixed, but really optimize the whole shape of the trajectory. So we don't fix any chunks of data, because if you start fixing chunks, then you don't improve the local precision within those chunks. Sorry. We're also doing optionally joint online calibration of all the required calibration info. So the extrinsics of the sensors and so on can be calibrated online. Here's an example of a result after SLAM. And this is after global optimization. And here's another example from the challenge data set. This is an area that is really far away from the area where the mapping took place. And initially it's a little bit noisy, but after global optimization, then the wall gets much tighter and much more precise, if you will. And in this way, we basically process all of the HILTI data sets and obtain the results that we achieved. So I was also asked to talk a little bit about the challenges. Sorry. In many existing methods and benchmarks, the results are inspected at a relatively coarse scale. For example, people use HILTI odometry. Sorry, I'm having some issues. People use HILTI odometry and look at it from 100 meters away, but there's little work in the literature that really looks at the registration quality at a very small scale. For example, sorry. So for example, is an individual registration result a little bit off, or is every single laser scan really undistorted and aligned as well as it can possibly be? Because sometimes small errors don't matter globally and the SLAM jumps back into the correct state, but sometimes they do matter, and then there is drift and loop closing is required. But loop closing distributes errors according to the covariance matrices, and these are difficult to obtain and often don't capture the true error distribution. Sorry. Sorry again. So effectively, loop closing bends the trajectory and tries to close the loop, but it's not really clear whether it does that at the correct spots. So despite having this great global optimization, there's still some dependence on SLAM, because some errors, there are not, it is not possible to recover from those, even with global optimization. Sorry. Really sorry for the voice issues. It's really hard for me to talk right now. Sorry, thank you. But thank you for listening, and thank you for HILTI for conducting the challenge. Please ask me afterwards if you're interested in more detailed info about the challenges.